All right, so hello, US familiars. Today we're just going to be talking about hypotheses and certain key points regarding them. First off, we just have the basics, how you measure central tendencies, the mean, median, mode. Everybody knows that. So the mean is basically the average. You're going to take all the numbers, you're going to divide them on the numbers. You're just going to take them all, divide them on the number, and just keep in mind that the mean in particular is seriously prone to be susceptible to outliers. So keep in mind if you have an outlier, if you have a very big number, a very small number, that would most significantly affect the mean. And this is a very high yield point for all your steps. You could be asked that. The median, you're going to arrange all your numbers ascendingly, and then you're just going to choose the number that's in the middle. Or if it's an even number, then you're going to choose the two numbers in the middle and then divide them to take the average. If there's a mode, regarding the mode is the most frequently repeated number. Okay, remember that the mean actually determines something called the skewing of the data. So when the mean, median, and mode are all equal, this is a symmetrical distribution. But if the mean is the biggest, then this is a positively skewed curve. If the mean is the smallest, this is a negatively skewed curve. There are measures of dispersion. You can use the range, interquartile range, quantile percentiles, standard deviation, standard error mean. The highest yield of these is standard deviation because this is the one that you're going to be asked about the most. But let's just go through them quickly. Of course, the range, you're going to choose the biggest number, smallest number, and everything in between, that's the range. Interquartile ranges usually refer to the 25th, 75th percentile. And then they would say, for example, something is under the 25th percentile, something is above the 75th percentile. So, and you could ask you about that, but that's not as significant. All right, this is basically the same thing. The standard deviation, this is what really matters. Remember that if we say, for example, something's within one standard deviation of the mean, that's 68% of the data. If it's two standard deviations within the mean, that's 95% of the data. So if, for example, you're being given a question on your step one exam, and you're asked how much of this data is above two standard deviations from the mean. So here's how you're going to think of it. You're going to think of, okay, two standard deviations, that involves 95% of the data. But that also, okay, so the 5% that's left, that involves 2.5% above the data set and 2.5% below the data set. So this is a very high yield point when it comes to your exam because you're going to be asked that question. And when you're stressed, when you don't have a lot of time, you might miss it out. So keep this one in mind in particular. Standard error of the mean is just basically one of those metrics that we use to see like the variation within the mean, but that's not, you're never going to be asked to calculate that. No one's going to be asked to calculate standard deviation. So it's not as high yield of a point. Again, this is our curve. This is our normally distributed curve. Focus mainly on the two standard deviation because that's the most important one. That's the most frequently asked one. When it comes to standard error of the mean, yeah, you can just ignore that for now. Now, variables, this is really important. There are two kinds of variables, right? There's the dependent and the independent variables. A dependent variable is when you measure, and independent is when you control. So, for example, if you're measuring, and this goes back to like chemistry 101. It's basically, if for example you have a flask and it's filled with water and a solute, and you want to measure how much it dissolves. When you heat the flask, in order to increase the ability of the solute to dissolve, the temperature that you're using, the temperature that you control, that's the independent variable. The amount of solute that dissolves, or the amount of solute that's still not dissolved, and you're just measuring how much of it ends up dissolving, that's the dependent variable. So basically, whatever you're measuring, whatever that is not under your control, that's the dependent variable. Whatever you are measuring, that's the independent variable. A null hypothesis, this is super, super high yield. In all published papers, in all published work, in all studies, we always refer to the null hypothesis. We never say, for example, a drug treats cancer. We never say that. What we say instead is, or X, for example, causes cancer. You'd never say that. What you'd say is that, there's 95% that the study that I did, where I used X as a factor to measure its ability to test cancer, was not due to chance. And most likely, this drug or this X factor was the cause of cancer. Saying that something is due to chance or the opposite of what you're trying to prove, that's the null hypothesis. And what we do is we reject the null hypothesis or we accept it. So this is a super high yield point. Now, there are some key concepts that we have to be aware of. There are certain types of error, type 1, type 2 error, statistical power, p-values. All right. So a type 1 error is, the way I like to remember is that you accused an innocent man. You rejected the null hypothesis, meaning you said that whatever is going on in your study is not due to chance, but in fact it's due to whatever you're testing. When that wasn't the case, it was actually purely due to chance. All right. Type 2 error. A type 2 error is basically a situation where you said, you know what I'm seeing is just due to chance, when actually there was a significant difference. When actually you should have rejected the null hypothesis. All right. Power is basically 1 minus beta, 1 minus the chance of causing a type B error. That's the power. Keep it simple and don't overcomplicate it. A p-value, p-values are basically the cutoff point, are basically the cutoff at which we say, you know, what we're saying is significant. So what we're trying to find in our studies is something that has a less than 5% chance, or less than 0.05. You know, like the value that, like, what's going on is due to chance is less than 0.05. And if that's the case, then this is not due to chance. We're going to accept that. So for all of biology, 0.05 is like the key thing. We're never going to choose another number. All right. So this is just a sum up, a quick sum up of what we're trying to say. All right, a confidence interval and p-values. Basically, a confidence interval is a range, and p-value is a cutoff point. And what you're trying to do is you're trying to find a situation, for example, where confidence intervals of two drugs or two parameters that you study don't overlap, just to say that, yeah, this is significant. Or a p-value that's under 0.05%, just to say that it's significant. That's what you're trying to do when you're solving hypothesis questions. There is the point of statistical versus clinical significance. Of course, something that is statistically significant doesn't have to be clinical, especially when the differences are very small or minute or they don't matter. Correlations, these are like certain ways to measure the data that you're doing. And the Pearson correlation, just understand it very simply, is that if things are not correlated, then you're going to find the graph to be dispersed. If with the points that you're measuring are actually correlated, they're going to show a pattern, right? So this is the pattern that we're talking about. Something that's very strongly correlated together, you're going to have a correlation coefficient of 1. That's the maximum. Something that's negatively correlated with each other, but still strongly correlated, is going to be -1. And something that is not correlated, you're going to have a correlation coefficient of 0. All right. So this stuff is like super, super, super high yield for all 3 steps. And this is actually the main point of what we're trying to talk about here. The parametric test. So if the variables that you're looking into are continuous variables, meaning you can put in decimal points between them, you're going to use a t-test if they're just 2. If they're more than 2, you're going to use the ANOVA. Okay. But if what you're talking about or what you're like studying is categorical, right? Meaning that something, for example, like boys and girls, something that is binary, that's 1 and 0, something that doesn't really like have anything in between, then that's a categorical item. So that in that case, you're going to be using the chi-square. All right, and the Fisher is the same for social samples. It's not really asked on USMLE. Like, it's very hard to find a question where the Fisher is going to be the answer for that. So basically, what you're going to be asked is always going to evolve between chi-square, t-test, and ANOVA. All right, so just keep this in mind. If your data is continuous, meaning if you can put a decimal point in your data, then you're just going to count them. If the number of data that you have, you're like comparing between just 2 things, then you're going to use the t-test. If you're comparing between more than 2 things, you're going to use an ANOVA. And if you can't put a decimal point, if what you're doing is 1 and 0 is binary, then you're going to choose categorical chi-square or categorical Fisher. All right. So this is another way to do it. This is like from Amboss. This is the best. Like I remember this. This really helped me a lot in my exam personally. And always thinking in the terms: is it categorical? Is it not categorical? If it is categorical, again, this is so important. Then you're just then I mean, if your independent variable is categorical, then you're going to use chi-square or Fisher test. All right. If it's not categorical, you're going to use something called logistic regression. The logistic regression part, you can kind of ignore it a little bit because it's not often asked. But just keep in mind that if usually what you're going to have a situation where the dependent variable and independent variables are both categorical, and they're going to ask you what to use, and you're going to use the chi-square. That's the most common thing. But if your dependent variable, what you're measuring, is categorical, what you're not measuring, what you're using, is not categorical, you can use the logistical regression. If what you're measuring can accept decimal points, meaning is not categorical, and how you're influencing the data is categorical, then you're going to use the t-test or ANOVA. If both of them accept decimal points, both of them are not categorical, then you can use the linear regression or correlation. Again, the correlation or linear regression, the logistic regression, are not as high yield as the chi-square, t-test, or ANOVA. All right, so I hope that made it simple, and thank you.